Well, if we have an acceleration vector, some of the acceleration could be along the tangent to that vector, and some could be normal to that vector. And we showed in Unit 2, Lesson 2, look at example 5, that if the length of a vector valued function is a constant, then the vector valued function dotted with its derivative is equal to 0. That's the number 0. Not much of a stretch to see that if the length of the derivative is a constant, then r prime dot with r double prime equals 0. In other words, really that's just the same thing, only applied to the derivative of the vector value function. So if the speed is a constant, then the tangent vector and the normal vector are orthogonal. If the object has a variable speed, this isn't necessarily so. As an example, the acceleration vector of a projectile always points down and would only be orthogonal to the tangent vector when it is at its maximum height. So at that instant you could think of the vector valued function for that instant is a constant, something like that. So, but there is a theorem that connects the acceleration vector and its relation to the unit tangent vector and the unit normal vector. And so I hope this wasn't boring to get through that.
Okay. That's okay. That's okay. Okay.
Well, okay. We will look now into the theorem. Theorem 11.4, it's about the acceleration vector. Actually, I guess we're in chapter 12. So the acceleration vector, if r of t is a position vector for a smooth curve C, and a normal vector exists, of course that means there's got to be two derivatives, then the acceleration vector, t, lies in the plane spanned by the unit tangent vector, t, and the unit normal vector, n. Now, how on earth would that be provable? And so we can start by saying, well, our unit tangent vector is the vector value function itself divided by its length. Sorry, the derivative of the vector value function divided by the length of the derivative of the vector value function. Because remember, unit tangent vector points in the direction where the curve is at that time, or actually how it's changing at that time. So that's the velocity vector divided by the derivative of the velocity, or sorry, the velocity vector divided by the length of the velocity vector. And so because of that, since we have that t equals v divided by length of v, we can say that v is the length of v times the unit tangent vector. So the velocity vector, you can think of that, and if you think about it, it's very logical that the velocity vector is how long it is times its direction. Right? Remember, this is a unit tangent vector saying this is the direction of the velocity vector. So the velocity vector is its length times a tangent vector in the direction of this velocity vector, right? So if you differentiated both sides of this, the derivative of the velocity vector is, of course, just the acceleration. And what we have on this side is a product. So we would use the product rule. The derivative of this would be the derivative of the length of the velocity vector times the tangent vector plus the length of the velocity vector times the derivative of the tangent vector from the product rule. Okay, now I think you would agree that the length of the tangent vector, length of t prime over the length of t prime is equal to 1. I guess I don't have any issues there with anybody. And the reason why I would do that is because the derivative of the tangent vector divided by its length is equal to the normal vector. I hope that's understood. In other words, this over this is the normal vector. So we've got that normal vector times this length of vector, t prime, times the velocity vector, length of r prime if you wish, the length of the velocity vector rather, and then the front part of that is the derivative of the velocity vector times the tangent vector. Now, since this is a linear combination of the unit tangent vector from this part, remember this is actually the derivative of a vector value function is going to be some scalar, and this is a scalar and this is a scalar function. So our vector A, the acceleration vector, is a linear combination of t and n. And since it's a linear combination of those two, it has to lie in the plane spanned by t and n. And often it's represented like this. The acceleration vector t is the part that's the tangential part plus times the tangent vector plus the part, the coefficient of the normal part times the normal vector. So the a of t is sometimes called the tangential component of acceleration, and the a sub n is sometimes called the normal component of acceleration. Note the a of t is whatever that turned out to be, and the a sub n is going to be the dot product of the velocity vector and the derivative of the unit tangent vector. But they can be more easily computed with the following theorem, and I think I'll put that in another video.